Once again, welcome to a new problem. This time we have a steel rod. Obviously, steel has iron in it, but this time we have uh, a steel rod like that with a specific length, which we're going to call L naught. And then also the other thing about the steel rod is that it has a cross-sectional diameter. The radius itself for the rod is r equals to 15 centimeters. We can always change that right away to meters by multiplying by 1 meter over 100 centimeters, and that gives us 0.15 meters. It's standing upright, and there's a man that's gonna step on top of it. Okay, there's a man that's gonna step on top of it. And this man happens to have a mass of 65 kilograms. Remember, with the mass we get, so this is 65 kilograms, and obviously his weight is acting downwards at mg, where g is the acceleration due to gravity. That's the information we're given. And in part A, we want to find well, this is going to be part A right here. In part A, we want to find the decrease in the rod's length when the man steps on it. So there's a compression going on because there's a surface there that's stopping the rod from going all the way inside the ground. So that compression is going to lead to a decrease in the rod's length, and that decrease, we're calling it delta L. Also in part B, the second part to the problem where, if there's compression, the atoms are going to move closer to each other. And we're saying, what distance is the interatomic spacing such that the atoms have a normal 2.0 times 10 to the negative 10 newtons between them. Or yeah, between the, or rather, instead of between, we're going to say the force, a normal 2.0 times 10 to the negative 10 normal force to support the man. So that's kind of what's happening in this problem. We have a steel rod that's supporting a man, and we want to find the decrease in length and also the distance. That distance, we're going to call it delta D. This distance, we're going to call it delta D. So we have delta L and delta E. So the initial part of the problem, again, we use equilibrium such that the force that's being applied upwards, that's supporting the weight, F equals to mg, and the mass of the man is 65 kilograms. We multiply that by the acceleration due to gravity, 9.81 meters per second squared, and that gives us 637.65 newtons. That's this force right here. And the question is, we want to calculate the percent decrease in length. The relationship between the change in length and the original length is equivalent to the force over pi r squared E, where this E is called the proportionality constant. The E is the proportionality constant. So what do we think about this? I mean, this R, we can make it small r. It's the same thing. It's just going to be plugged into that formula. So from that statement, from that relationship, we're able to determine that delta L is delta L over L naught, which is the percentage change in length, okay, or percentage decrease in length, percentage decrease in length becomes the force, which is 637.65 newtons, all over pi r squared, which is pi, the radius is 0.15 meters squared out, times the proportionality constant, which is 200 times 10 to the 9 Newton per meter squared. When you solve for that, you get 4.5 times 10 to the negative 8, and we want to multiply that by 100% because it's a percentage decrease. And so delta L over L naught becomes equivalent to 4.5 times 10 to the negative 6%. That's the percentage decrease. On the next page, we move on, and this time we want to get the percentage change in interatomic distance. So delta D as percentage, or rather not percentage, this is just your regular change because it's a delta, change in distance between the atoms, the distance between the atoms. So this is delta D over D naught. D naught is the original distance, equals to delta L over L naught. In the previous page, we were able to solve that portion, and it's given as 4.5 times 10 to the negative 6. Actually, in actual sense, it's 4.5 times 10 to the negative 8 before you introduce the percentage. So this part is 4.5 times 10 to the negative 8. And so if I want to get delta D, I have to multiply both sides by D naught, which is the original distance between the atoms, and that's given as 2.0 times 10 to the negative 10 meters. So delta D is 4.5 times 10 to the 8, or negative 8, and multiply that by 2.0 times 10 to the negative 10 meters. This ends up being 9.0 times 10 to the negative 18. We want to change that. So delta D becomes 9.0 times 10 to the negative 18 meters. That's your delta D. So once again, just a quick recap. There are two different units we want to compute. The first one is the change in length, or percentage decrease in length when the man steps on top of the rod. And then the second thing we want to compute is change in the distance between the atoms, the atomic. The normal force between them is 10.2 times 10 to the negative 10. This should be meters, I think. So it's 2.0 times 10 to the negative 10. And so we end up getting delta L over L naught. We saw for the percentage change is 4.5 times 10 to the 6%. And in the next part, we are supposed to solve for the change in distance between the atoms. And we use the relationship between at the atomic level and at the macro level, and we compare those two units. The other thing you want to remember in this formula right here, this is the E, and E is the proportionality constant. And so we end up solving for the change in atomic distance between different atoms to be 9.0 times 10 to the negative 18. So I hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.